Hello everyone. So in today's video, we're going to learn about RAG, which is Retrieval Augmented Generation. I think it's a very important topic because large language models are trained to a certain point in data, right? So there is a lot of pre-training that happens for models like GPT-4o, Gemini, GPT-5, etc. And in order to provide access to these large language models with our data, right, which could be proprietary data, and you don't really want a model being trained on that particular data. I mean, you could actually do that with a process called fine tuning, but that's expensive and unnecessary, and that's where this retrieval augmented generation concept became really popular. Idea of this video is to walk you through how exactly RAG works under the hood, and at the end of this video we will be creating this kind of an application, so you should also be able to do this. So ignore some of the terms for now, they will be clear as we go along, but let me first put a vector store name. So I want the data that I'm going to get uploading to this particular application to be stored somewhere. So I'm going to call this YT store, just as an example. Next, I'm going to select the PDF file. So I have selected one PDF file called what is RAG. So let me open that. Let me just show you what that file is. So basically, it's a retrieval augmented generation for large language models, a survey. It's a paper by Arxiv, and it has about 21 pages. Now, uh, traditionally, if we wanted to learn about this paper, you would go into each of the sections, read it through, etc. But with the power of something like RAG, you could actually leverage a large language model to be able to provide you responses about this particular paper. And that's exactly what we are going to do. So I've selected the vector store name, I've uploaded the file. Next, I'm going to click on create vector store on OpenAI because that's the storage what we are going to be using throughout this video. So let this get created. So if you can see that it's creating a new vector store is created, and then it's uploading the files to your vector store. Once that is done, you have the chat interface ready to go. And now I'm going to ask a question that what does the paper say about advanced RAG? The model is going to kind of think, use retrieval augmented generation to actually go and find the relevant information from that paper, and then basis of that it's going to provide a response. So it's saying the paper discusses advanced RAG as part of a comprehensive review, and as you can see, it's very easy for us to kind of do a very natural language kind of interface with that particular document. Now you can challenge saying that there are so many existing tools, right? You could just go to ChatGPT and do this all by yourself, but that really doesn't teach you how exactly it's working, right? So there's a beauty in kind of trying to build it out yourself so that you have a thorough understanding of how these things work under the hood. You probably know coding. If you know, great. If not, I will try to simplify this video as much as possible so that you are able to follow along. And yeah, let's kick off. Okay, so first let's try and understand what is RAG. Okay, so on the screen, what you can see is, let's say a user is asking a question, commonly referred to as a prompt. The first thing that would happen is, based on the user query, the relevant information that the user is asking about is retrieved from your data source, a vector database in this scenario, right? So basically it creates a search and retrieves the relevant information. Once this information is retrieved, it is passed on to a generator. Now the generator is a large language model in this case. So the large language model typically gets two inputs. One is the user query, and second is the information that it retrieved based on the user query from the vector database. It then augments both those pieces of information, and basis of that generates a response. Next, let's see a pictorial representation of a vector database. I'm sure, I mean, it's very, very complex in reality, but this is a simplified version. So when a particular search query is passed to a vector database, what it does is it returns similar items based on their semantic meaning. By semantic meaning, what we are trying to say is, let's say your query is about a pet. Okay. In that scenario, the vector database is actually not going to just provide results where the term pet exists, but it would semantically understand that a cat or a dog could also be a pet. Basis of that, it will retrieve information from the vector database semantically rather than the exact term matches. Now, this is not entirely true, but typically, when you pass a search query to a vector database, you have three options. One is a keyword search. So by a keyword search, it is actually looking for that term itself. So if I'm searching for animals, it would search for animals. The next is the semantic search that I just explained, where it looks for the meaning rather than the exact term. And then there is something called as hybrid search, which is a mix of both. Another thing that is kind of a characteristic of a vector database is semantically similar terms are very close to each other. How does that happen? We will find out. But for now, just understand that, let's say something like apple and banana and fruits all will be very close to each other in this vector dimension. All right, so now let's try and see one example in action so that it becomes really, really clear to you that how this entire process works under the hood. So let's say you have a PDF document which has a lot of recipes. Now, this PDF might be having multiple pages, 50 pages, 100 pages, etc. For any embedding model, so one example is text embedding 3 large from OpenAI, has a context window length, which means it has a limit on the number of dimensions that it can handle. Hence, it is impossible for that model to convert a piece of text that is too large in one go. To handle that problem, what we do is we break the PDF into multiple sections of text, commonly referred to as chunks within the RAG terminology. So let's say this recipe book is broken down into chunks, and each chunk represents one recipe, right? So paneer butter masala could be one chunk, kadai paneer could be another, paneer tikka masala could be the third chunk, and so on. Now, the next step that would happen is this particular chunk of text gets converted into their vector embedding, which is a numerical representation of actually what that text is about. Because, like we said earlier, vector databases cannot store text. They can store mathematical values so that mathematical operations can be performed on them when we are trying to retrieve the relevant information. So how does this happen? The chunk of text will first get tokenized. And again, what is tokenization? We will see through code, which is nothing but a numerical value for each word within that chunk of text. So what this results in? It results in a sequence of integers or token IDs, and then these IDs are fed to that embedding model so that it can be converted into an entire signature for that particular uh, text, right? So it's more like a semantic fingerprint of that entire chunk. Now, while this is happening, uh, we also need to ensure that when we are storing these specific chunks, the model is using something called as multi-head attention to weigh the importance of each token relative to the others within the same chunk. So the example that we spoke about earlier, where fruits, banana, orange, etc., if it all exists within that same chunk, this is where the model will actually use the multi-head attention and then position them in a way that they end up being very close to each other within the vector database. Another example could be a token for bank will have a different vector representation if it appears near river versus if it appears near money, because both of those could have a very different meaning for bank. But this is where actually the model is taking care of it. Okay, so once this semantic fingerprint is created, the recipes or each chunk are stored as embeddings in the vector space, and these will be obviously clustered by semantic similarity. So actually what we are storing in the vector database is mathematical representations of meaning, and a lot of heavy lifting, if you see, is being done by the embedding model. Moving on, so this is basically the creation part. Step two would be searching the vector store. So how does that happen? So let's say the user query is, give me a smoky paneer curry that is mildly sweet, buttery, but also spicy like kadai. Now you cannot really control what a user might ask, and obviously this particular query or prompt is a mix of two recipes, two or three recipes. So one thing that we need to understand is this query is not searched as text, because what we said earlier is the whole idea of converting into a numerical representation is that so that we can perform some sort of mathematical operations on this stored content. So the query is first converted into the vector embedding. And one thing that many people might go wrong with is the model that you used for creating the embeddings. The same model needs to be used for querying or conversion of the query into its vector representation. If we fail to do that, it might affect the accuracy of the retrieval process, because not every model uses the same tokenization or doesn't convert text into token IDs exactly how the other model would, right? So this is something that you have to be very, very sure about. So once this is converted into its vector representation, the OpenAI vector store is what we are planning to use, but obviously these could be other vector stores as well. What they tend to do is they will compute the distance between the query vector and each of the recipe vectors that it has stored. Now, this is done by using metrics like cosine similarity or dot product. Cosine similarity is the most common right now. Now, basis of that, it is going to retrieve those chunks, and what actually gets retrieved is the text element. So basically, there should be some sort of decoder to again convert the retrieved vector embeddings into its corresponding text data. But this is how a retrieved data would typically look like. So there would be the chunk. You would have some identifier for that chunk. There would be the actual content of the chunk, that what is the text element within that chunk. And then there is also an associated similarity score based on the algorithm that you're using, right? So cosine similarity will have some sort of similarity score, basis of which it is going to rank. When you are actually passing that query for search, you have a variable sometimes called as top k, sometimes called as max results, depends on the vector database. But that is the number of chunks that you wish to retrieve when you are passing the search query. Okay, so thanks for bearing with me going through this. The last part where everything comes together is the augmentation. So basically now what is happening is you have a system prompt that you are passing to your large language model. So let's say you are a professional chef assistant, could be one example prompt. You pass the context. Now context is what got retrieved as part of this search. And then there is the user query, which is give me smoky paneer curry that is mildly sweet, buttery, but also spicy like kadai. Once the large language model has all this information, it is going to identify the overlapping concepts, create a new recipe, and it is entirely grounded in the chunks that were retrieved, right? So it's not really using its own knowledge, but rather it's using the content that you provided the large language model. Obviously, in terms of keeping it more grounded within the system prompt when you pass to the large language model, you should also add a line that says, please only generate responses from the context that we provide. And then there are some prompt engineering techniques of how exactly you can pass that context within the system prompt. And this would be a example output. Clear? Okay, so I think in terms of theory, this is all that I wanted to cover. Now in the following video, we'll get into the coding part. Okay, so the first thing that we need to do is clone the repository from GitHub. So I've already created the GitHub repository for all the code scripts that we are going to run through in this video. Right, I'll put the link in the description. Um, the next step that we would do is open Visual Studio Code. VS Code is a IDE to do development for different code languages, and it's easy. I mean, you can just search for Visual Studio Code and get it installed in your system, right? So once you open VS Code application, this is the screen that you should be able to see. The first thing we want to do is click on terminal, hit new terminal, and you could use PowerShell or Bash, but I prefer using Git Bash. So if you're following along and new to coding, I would recommend you also do the same. The first thing I would do is type this command pwd to see which folder I am in right now. Right now, you could have different folders, or your structure might be different in your system. So if you go to File Explorer, you should be able to see C, D, right? So similarly, you might have different names for the drives. I generally do all the coding in G drive. So I'm going to navigate to CD, G colon, and hit enter, and just double check that I'm in G drive now. So it tells me that I'm in G drive. The next thing I would do is go to the GitHub repository, click on this green code button, and you should see this clone and then the HTTPS link, right? So we'll copy this link, go back to Visual Studio Code and type this command, git clone space and the URL that we just copied, and I'm going to hit enter. So this is basically going to clone and bring all those files into your local system. Now we are already in G drive, so you can type this command ls and it will show you all the different folders that are there, and rack search, which is the name of the folder that we just cloned, should be visible there, right? So you can see rack search. Next I would do is cd space rag dash search and hit enter. So now I am in the G rack search folder. So this is the first step. Now in Visual Studio Code, you click on File and click Open Folder. Then you navigate to G Drive and search for Rack Search. So I'm just going to click on this, just select this folder, Rack Search, not double click, and then hit select. Once I do that, you should be able to see all the files that got downloaded. And you might get a message that do you trust this folder, etc. You just click on yes, I trust or trust, right? Next, what we want to do is just click anywhere on this left pane, and then on your keyboard hit the Control, Shift, and P button together. Right? So you have to keep Control pressed while you press Shift, and then Control and Shift should be pressed while you hit the P for Python button. Right? Then you should be able to see this Python create environment option. If it's not visible, you can even search for this. Right? And I'm gonna hit that or select that option. You can either use Conda as your virtual environment or VENV. So I'm going to use VENV. Select that, your interpreter path. So Python also should be installed in your system, Python 3.9 or above. And then all the dependencies that are needed to run all the scripts, right, are already there in requirements.txt. So while you're creating the virtual environment, so basically what virtual environment does is we will do all the or we'll run all the scripts through the virtual environment, which will hold all the dependencies that are needed to successfully run the code, right? So I'm just gonna tick on this checkbox here so that everything that is there in requirements.txt will get installed. So I'll hit OK, and I'll just quickly show you. So this is basically the requirements.txt where you see all the different libraries that we need to install in order for all the scripts to work, right? So I'll just come back after the environment is created. Okay, so the requirements or the dependencies have been installed and the virtual environment is created. So you can verify that by seeing this VNB folder being created. Next thing you want to do is update the sample.env file. So just right click here, uh, select rename and just get rid of sample. So the name of the file should be .env only. And we would need the OpenAI API key and the Tavily API key. So let me navigate back here and you can type platform.openai.com. Obviously you should be registered on OpenAI. So once you come to this, you need to log in to your account. So I'll just quickly log in and come back. Okay, so now that I have logged in, I would click on dashboard, and on the left navigation pane, you should see API keys as one of the options. So I'm going to select API keys and let me create a new key. So I'm just going to call this rag search 1 because I already created one rag search earlier. So I just select this, keep everything else as it is, and just hit create secret key. This key will be created. Just copy this, make sure you copy it now because once you click on done, this key will go away. Then you might have to generate a new one in case you haven't copied. So before I even click done, I'll go back to Visual Studio Code and enter the key right here. Hmm. Next, I would go back to my browser and go to Tavily, app.tavily.com. In that, you would get an option of creating an API key, and this is free. So I think Tavily allows you up to 1,000 credits, and Tavily is nothing but a web search API, right? So it allows you to do web search because we'll be using some web search components in one of the scripts as well. So good part about Tavily is you can actually copy this key later as well. So I'm just gonna copy this key which I already created. To create a key, it's simple. You just hit plus, give the name, and then click create. And so I've copied the key. I'll go back to VS Code and then enter the Tavily key here, right? Just make sure that you keep saving the scripts every time you make changes. So for the .env also, just do Control S so that it gets saved. Most of the things that are needed for the setup are already completed. I can close this. I would again go back to terminal, click on new terminal, and you can see this .venv which is already here. Now I personally am going to use git bash again because I prefer that, but here also you can see that this .venv shows up, which means that I am executing all the scripts, Python scripts, within the virtual environment. Just as a fail safe, you can also just type this command source .ve, sorry, source .venv slash scripts and just hit tab, so it automatically will complete that. Sorry, I just .venv scripts and then activate. Yeah, so you don't need that slash before the dot. So .venv scripts activate, hit enter. That would ensure that you're executing all the code from within the virtual environment. So with that, I think we are set up to start running through all the different scripts. Okay, so first let's look at the embedding concept, right? So conversion of text into embeddings. Now, this is not a single word, but rather a string of text. And based on what we spoke earlier, it could be a chunk with a lot of characters and words. So for this particular script, we are firstly going to import OpenAI, import OS and .env so that we can load the environment variables. And then I'm also going to import tick token just to show you the token IDs for the input text that we are going to pass here. Now, you don't really have to worry about this. This step is completely independent of the embedding model converting something into their vector embeddings because the model takes care of it, but I'm just going to print so that you have a better understanding of what those token IDs look like. Tokens, I mean, why tokens is a very, very big question. And if you're interested, you should definitely research that. But initially, when researchers were trying to train these large language models, they thought that they can go with the approach of English characters. The problem is that with characters, one, that the sequence becomes very, very long because you're talking about words and also semantic meanings of those words, right? It was very difficult to scale with that kind of approach. They also tried word level modeling, but again, there is a massive vocabulary, millions of words, and it is not going to be able to handle new or misspelled words. So finally, they kind of came to the conclusion that the best approach or the middle ground would be using something like tokens, because tokens actually break down words into some common themes. For example, a word like unbelievable can actually be broken down into un, believe, and able. And each of these terms will have their own token IDs. Because of which, what happened was the vocabulary size became much more manageable. It could actually represent any word, even words that are unseen. The sequences, so shorter sequences than characters, and it also provides a better semantic signal and better GPU utilization for the transformer architecture. And again, like I said, feel free to research this area, that why really tokens. Like everybody talks about tokens, even any API call that you make to OpenAI, it shows you input tokens, output tokens, and why this entire jazz about tokens. Please do research that as well. Right, so we're going to basically print the input text. We are going to tokenize the output, and tick token basically is the library that we will use for encoding into the respective token ID. Then this token will get decoded and we will display it so that you are very clear that for each term, what is the token ID. Next, we would create a variable called res or result and create the embeddings. And then obviously the embedding vector is going to be pretty long. So we are only going to print the first 10 values for that. And one thing that I spoke about earlier in the video was that every model has a different limit on the number of dimensions that it can handle. So we'll also print the dimension and we'll change the model. First, we will do it with text embedding 3 small, and then we'll change this to large to see the differences. Right? So let me run this code. So Python text embedding.py, and if you see, the text is how to bake a cake. So this is the output that we are seeing. So let me just bring this up a bit. So input text, how to bake a cake. The tokenizer output is the token IDs, and it has broken it down into 6 different token IDs. So how is this, to is this, bake is this, is this, cake is this, and then question mark is this 30, right? And these are the decoded corresponding tokens. This is the embedding vector that got created, right? And this vector basically is created based on a lot of things. So obviously the tokens, and also taking into consideration, are there any semantically similar terms? So it is basically that semantic fingerprint that you see here in terms of the embedding vector. And this is the full vector length of this model, which is text embedding 3 small. So let me change this to large now, and let me save that. And now if you see, few things might change. Yeah, so the first thing that you would see is for both these models, at least the token IDs haven't changed. So both of them have kind of been trained on the same tokenization method. Decoded tokens obviously same. The generated embeddings are little different because we are printing the first 10. But here if you see, the full vector length is 3272. Oh, sorry, 3072, 3072. So it's almost double of the text embedding small model. Now this is a more expensive model, text embedding 3 large, but it does perform better because it can handle larger uh, length of text, right? So what happens if you go beyond the limit of the model? The text is truncated and dropped, right? So you just lose whatever value was there within that particular chunk, and hence you have to be careful what is the chunking strategy that you will use for creating the vector embeddings. Next, let's look at creating a local vector database. Now, it is not mandatory that you have to use OpenAI Vector Store. Uh, if you wish, you could also do this with a local vector database. So let's quickly go through the script. Again, standard import OS and .env for the environment variables. We're going to be using LangChain. So we'll be using the LangChain PDF loader. We're going to use OpenAI embeddings to invoke the OpenAI embedding model. We're going to use a recursive character text splitter to actually split the text into chunks. And then we are going to import FAS, which is the FAS index by Meta, but it will be created locally within your environment. So first, obviously, you load .env and pass your OpenAI API key. Next, you create the vector database. So this is a function to create the vector DB. So we're going to print couple of things. One is creating a vector database from PDF file, loading PDF. We use PyPDF loader to load the actual file. docs equal to loader dot load, and then we print that okay, the docs have been loaded, length of docs in pages. Next is the chunking step, right? So this is where we will create chunks, and this is basically what is commonly referred to as the chunking strategy. Now, many a times in an enterprise environment, you have to kind of play around with this a bit to understand which chunking strategy really works well for you. Now, this could be a whole other topic to discuss chunking strategy because there are so many, right? There is also something called a semantic chunking, there is fixed size chunking, there is markdown chunking, and a lot of different strategies. Here I'm showing an example of fixed size where I am telling uh, the code, or rather I'm dictating in the code that you keep a chunk size of 800. So that's basically 800 characters and an overlap of 100 characters. Now, why is overlap important? Because sometimes what would happen is, let's say, uh, fixed size is pretty random, right? So my PDF has 10 pages, 800 characters could truncate at any minute. And then maybe it's part of some continued paragraph which automatically then goes into the next chunk. Now, I don't want to lose continuity of that particular paragraph. Hence, I put in some overlap. So what this would do is it would create a chunk size of 800, but then also consider that 100 is reserved for a overlap. So the last 100 characters of my 800 chunk size would actually be the first 100 characters of the next chunk. And that's why overlap is important, and that's why you have to play around a bit with your chunking strategy. Then basically use the splitter function to split the chunks, and then you say that okay, from this particular document so many chunks were created. Once that is done, you finally create the embedding. So you use OpenAI embeddings, pass the OpenAI key, and select which model. So we are going to select text embedding 3 small, vector db equal to fast dot from documents, and then you pass the chunks which we created here and the embeddings that we'll get from here. Basically, you save the vector database, and here it is vector db dot save local vector db path. So currently in my file, you will see that or within this particular folder, there is no vector database that is created. But once we run this, it's going to create it. Then we initiate the program if name equal to main, and the PDF file path. So I'm going to use this recipes book.pdf, and the vector db directory I will pass again dot, means within the same folder create something called as a vector store, and then finally create vector db, right? So let's run this. Okay, so let me just show you the output. So first loading PDF, loaded 24 pages. So that's the number of pages that are there in my document. Chunking documents. So it created 45 chunks. Post that it generated the embeddings. After that, basically it ran this saving vector database, and then the vector db saved to dot vector store. So now if I go here, obviously I'll not be able to see anything, but I can see there is a index.fas and index.pickle file that got created. Okay, so now that the vector database has been created locally, which you can see here, we will write this script to search in that vector database. Okay, so standard imports, we will need the OpenAI embedding import here because we have to convert the user query. Because this is search, there will be some user query that will be passed. That also needs to be converted into its vector embeddings. And then the distance needs to be calculated between the query and what's actually stored in the vector database, which we did in the earlier script. Right? Here we do the load.env, use the OpenAI API key, vector db directory, that's the path to your uh, vector database, which is here, and then you load the vector store first. So basically you pass the embeddings, OpenAI embedding, pass the model, which is text embedding 3 small. Again, please remember that the model that we used to create the embeddings from our document, we will use the same model here because otherwise we will not get good results. Then we create the vector database fast.load local, and we pass the vector DB and embeddings. Right? This is the similarity search step. So the query that we will be passing is recipe for bread pakoda, and then results variable vector db dot similarity search, and here we will pass this query and k equal to 3, which if you remember is the number of results that will be returned based on the semantic similarity, right? For OpenAI vector store, this is passed as max results. So depending on vector store, uh, this might change, but for FAS it is K. If I change this to 5, I will get top 5 results. Then finally we print the search results. So let's run this, and let me make this bigger. Okay, so what you can see here is it's giving you the results. It shows you what is the actual content of that particular chunk, right? And this is where my chunk size or chunking strategy actually comes into the picture. So this will be in and around 800 characters is what we had selected. And then every chunk will also have a associated metadata, which is really important in some cases, because what happens is this source that you see, right, it's actually showing me the file from which the response was taken. So there is a concept known as citations. So generally in RAG, if you're using a large language model to generate a response, you usually tell the large language model that please also include the source of your information. So when the answer is returned to the user, citations or sources are provided so that the user is also sure that the response has been actually taken from the document that the user had provided. So here you have, I think, two results which it found semantically relevant. Now that we have seen how we can create the vector database locally, let's use a much more advanced solution, which is the OpenAI vector store. In order to actually navigate to the vector store, because we will be needing this, all you need to do is go to platform.openai.com, and once I go to the base URL, what I need to do is go to my dashboard, and within manage you should be able to see storage. So you go to storage, and that is where you will be able to see the vector stores that we will create on this OpenAI vector store. So let's go back to the code and quickly go through the script. So again, from OpenAI, import OpenAI os.env. We're going to import time as well. Load.env, pass the OpenAI client, and then initialize the client here. Right. Vector store name, I'm going to pass recipes dash book dash vector store. So it's going to be the same file that we used for the local FAS index. Then we are basically going to just ensure that that vector store doesn't exist already. If it doesn't exist, we will create a new vector store. But this is basically just looping through the existing vector store names and checking if it exists. If it exists, it will reuse the same store ID. If not, it will create a new one. Now the chunking strategy I'm passing here manually. You don't need to pass this because OpenAI will kind of default to some values on its own. But I wanted to show you that we can also pass this. So the chunk size I'm going to pass is 800 and overlap is 100. Again, same as what we passed for the local FAS index. Then we will upload the PDF with the static chunking strategy, right? So client.vectorstores.files upload, vector store ID equal to existing vector store ID, file open, and then we pass the uh, location of the PDF that we want to pass. The chunking strategy we're going to pass here. So once this is done, it's going to print saying successfully added to the vector store. Now, what I have seen is if I try to create the vector store and do the similarity search test at the same time, it doesn't work because probably it takes a couple of seconds for that to actually get uploaded to the OpenAI vector store. So I'm just going to comment the last part out. And first, let's just create the vector uh, database. So I'm going to run this code, Python create OpenAI vector store.py. So first it's going to check if it already exists. And obviously it didn't find one, so it's creating a new one. And then it says uploading PDF to vector store with static chunking strategy, and the vector store has been successfully added. So if I go to my OpenAI vector store and let me just refresh this. Yeah, so you can see recipes book vector store is created now. You can see the size 38 KB. That means there is data already there. And the file that it has used is recipesbook.pdf. Okay. Now let's try to search, and I'm going to uncomment this part. And let me pass the recipe for bread pakoda in this case, right? It's the same query that we passed. And here if you see max num results is what we are passing instead of k that we passed in the FAIS index. You can also pass ranking options. So score threshold, basically what it means is I don't want to look at any results which have a similarity score of less than 0.75. So anything closer to 1 is the best, and as it comes lower, that means the chunk that is being retrieved is not that semantically relevant. Again, there is one other advanced concept around re-ranking within a RAG framework. So what re-ranker generally does is when you first fire a query, it's going to use something like a cosine similarity to find the most relevant chunks. So let's say it found 50 relevant chunks. What a re-ranker does after that is it again compares the meaning of the user query and then tries to re-rank those top 50 results, which are based on similarity score, to make it even further semantically relevant to the user query. I'll not go deep into that concept, but if you want to read about it, please do read about re-ranker in RAG, right? Or in retrieval. It's a very interesting concept and it does prove to do much better as opposed to just relying on cosine similarity. Hmm. So here OpenAI vector store kind of does the ranking for you, and you can pass this as auto, right? And then finally we will print the search results, and let's see how this works. So let me clear this. And I can actually run the same file again because it'll check if that vector store exists, which in this case it would now, and then only run the search. Okay, so vector store found, reusing the existing store, testing similarity search, and these are the search results. So this is the data, you have this content, right? Again, you can see bread pakoda is already there in this, but then there will be top 3 results, and each of these will have some score associated with it, and it will also have the metadata. So if you can see here, it has something called as file ID, the file name, which is recipesbook.pdf. It has the score. So I think I hope it is clear to you that how exactly this retrieval part is working. In the uh, next section, we'll kind of look at how this kind of ties together with a large language model. All right, so now let's look at how this entire thing stitches together when we put a large language model in the loop. Okay, so the imports, import OS, import.env, from typing import list, from OpenAI import OpenAI, and then from LangChain OpenAI import chat OpenAI. So we're going to be using, I mean, this is not really a agent that we are building, but a very raw implementation of a RAG. Okay, so we load .env so that we can read the OpenAI API key. OpenAI client is initialized here. We pass the vector store name. So the vector store that we created, recipes book vector store. This is just a lookup to just confirm that the vector store exists. Next, you define a function for RAG search, and here you basically generate this response, OpenAI client dot vector stores search. So you're passing in a query to this function, and it will return the result from that search. So if you see, we are passing max num results as 3, and the ranking options we are passing score threshold of 0.75, ranker auto, pretty standard to what we are using in the earlier script for search. Now we are going to do a bit of unwrapping and parsing for the information that we find from that search result. And then finally, we are going to return the content, and we are also going to return file name. So file name is again tying back to the citation point that I had brought up, because we want to kind of understand exactly what the file name is from where the answer has been provided by the LLM. Here we initialize the large language model, so we're going to use GPT-4o mini, and then we're going to run the program logic. So here the query that I'm going to pass is show me the recipe for bread pakora, and we'll print searching vector store for that particular query. We get the results, and then we are just doing some sort of formatting of text so that the answer is much more clearer for us to read. So we're going to basically create this sources string and uh, kind of append it at the end of the response, and this is the prompt, right? So here basically you're passing your helpful assistant, use the following information, and then you're passing the context, which is the result that gets retrieved from that search function that we have written, and the query, and then finally the answer. So basically we'll generate the response, and then response equal to LLM invoke this prompt that we have built. So let's run this Python rag example.py. So it found the vector store because that's something that we had just created in the previous script. And now the LLM is kind of doing the augmentation part, right? So it has the query, it has the results, and basis of that, this is the final answer. So here is the recipe for bread pakora. These are the ingredients. For the filling, use this. The method is this. Because it found some nutritional information, it's also showing that on the screen. And source bread pakora, and sources, which is the file that we want to kind of show as citations, is recipesbook.pdf. And this kind of reassures the user that okay, whatever response is being generated here is actually coming from a valid file, and hence I know that this response is grounded. Okay, so now before we jump into our next script. The first thing I quickly wanted to walk you through is what is LangGraph, right? Because this is going to be relevant. Obviously, this video is not aimed at giving you a full rundown of LangGraph right now, but it's important to understand the next script. So just at a very high level, we'll try to see what LangGraph is, right? So LangGraph is nothing but an open source library. It's sort of a framework that is built around AI, and it allows you to address one of the key problems with large language models. So large language models are stateless. So if any query I pass to a LLM, it's not going to remember the previous context or the previous conversations that I had. So LangGraph kind of helps you maintain that state within an agent that is actually leveraging a large language model. So what it does, it basically creates a sort of a workflow with a graph architecture. So if you look at any sort of graph, it has, and this is basically from a statistics perspective. So a graph would have nodes and edges. And within LangGraph, what you are able to do is create nodes. So if you look at this flow chart here, right? When we start, we kind of start with the initial state. Now that state could have a lot of different elements. So it could be features like, or it could have a user message or system prompt. It could have the AI response. It could have certain responses from the tools that were called by the agent, the actual tool execution, etc. So all this state is kind of maintained within LangGraph, and each of these tools or agents are sort of nodes within that graph. And obviously, because it is sort of a graph architecture, it would have edges too. And edges are basically moving from one node to other. So in this simple flowchart, if you see, we start with the initial state. The first node that we would go to is the agent node. Now, agent has been equipped with a large language model. So the large language model is going to think that, okay, what is the initial state? What is the expected action from my end? So it could have a system prompt. It could have a user message, the user prompt, what the user is asking about, and basis of that the large language model is going to take certain actions. So it would have edges that take it to the next node. So now within this you see there are two nodes. One is end and the other is a tool node. So tools are nothing but functions that we are going to provide to our agent. In our case, because it is RAG, we are going to look at RAG search as one of the tools that we will be making available to our agent. Now, agent and LLM, this particular step kind of just tries to understand what is the user query, and the LLM has already been equipped with what tools it has access to. So the LLM actually decides what is the next step that I will take, and basis of that decision, you draw the flow to go to the next node. Let's say the LLM realizes that, okay, if the user is asking about a particular recipe and I have access to a RAG search tool that can help me, get information about that recipe. So the LLM will decide here that, okay, I am going to use the RAG search tool, and basis of that, it will traverse through this edge, come to this tool node, and then the actual tool execution would happen at this node. So once the response is taken from your RAG search, it would feed that back into the agent. And the next thing that would happen is your state gets updated with this latest information. So the information comes back to the agent. The LLM thinks again that, is this sufficient information? Is the current state enough to provide a response to my to the user. If it feels yes, it is sufficient, it would then go to this end step and provide the final response. Right? I think it was important to kind of cover this so that you fully understand LangGraph a bit. Obviously, it's an entire topic on its own, but at least they should give you a fair understanding of the next script that we will be running. We kind of try to understand what is LangGraph at a very high level, but let's just look at this Python code. So what I really want to introduce here as a concept is agents, and LangGraph kind of makes it very easy, as we saw on how you can build, deploy agents, provide access to uh, tools to that particular agent, add memory component to the agent, and a lot more. So this framework is kind of really going hand in hand with all the AI development that is happening parallelly. Mm. And in this particular script, I am adding another tool. So what we have seen so far is RAG search, but just so that we understand that concept of nodes and edges, I have added one more tool for web search. So let's look at the script. So first we kind of import certain libraries for the code to work effectively. So from typing, we're going to import a couple of libraries, osn.env standard. From LangGraph, we are going to, if you remember the state part that we spoke about, right? So import state graph, and start and end are nothing but nodes, right? So if you see here, start would the first maybe virtual node in graph style. Same goes for end, the last maybe virtual node in graph style. Then we have LangGraph messages, import add messages, again a very useful kind of library which allows you to append messages to the state of what LangGraph is currently maintaining without losing the previous context. The tool node, again, we spoke about that. Uh, from LangChain tools, import tool. This is just to make sure that we are able to pass tools to the large language model. So there is something called as tool binding that we will be doing with the large language model. Obviously, OpenAI we need access to those models. From core messages, human message, system message, again type of messages that get stored within the state for LangGraph. From OpenAI, import OpenAI, and tably is what we will be using for the web search element. So first obviously we do the load.env, and here I have to pass one additional key. So we have been passing OpenAI API key all this while, but now we also need to pass the tably API key, which will be used for the web search. Then we initiate the client. So OpenAI client, pass the OpenAI key, and then we define this variable LLM and use chat OpenAI because we want to initiate the chat with the large language model. And here we can define the model and the temperature. Vector store is something that we have already seen. So we are still using the OpenAI vector store here. And for the vector store name, again, we are going to be using recipe book vector store, store ID. So basically this is going through the list and just making sure that this vector store already exists. We'll also print that using vector store ID is what we're doing. Tool definitions. So here is where the LangGraph kind of allows you to use this decorator called at tools. So basically these are going to be the tools that we can pass to our agent. And there are two tools, like I said. One is the RAG search, which we have seen so far, how this works. And another tool that we will add is the web search. So basically, Tavily API allows you to do couple of things. One of them is obviously web crawling, web scraping, web search, and a lot more other things you can do. It's a pretty fine service for searching the internet, and if you want latest information available to your agent, generally web search APIs are used. There are other options like Bing search, SERP, which is from Google, which could also be leveraged, but we are going to use Tavily. So here is where the web search results will be kind of retrieved based on the query that the user is passing. Then you have the class agent state and type tick. Now this is little important because what we are trying to do is we are trying to maintain some sort of state where we have uh, the system message, the human message, the AI message, the tool message, etc. So all these things are kind of going to be maintained within the state. The reason why we do annotated is because we want to have the additional metadata for that particular uh, element or message within the state. So basically the type is a list because it is a list of messages, and this add messages is what takes care of adding new messages to the state without losing the previous one. Right? Then basically you initiate the system prompt. So here what we are saying is you are a helpful assistant that must use both tools to answer the questions, and then we are giving it very explicit instructions like first use the RAG search to find information from internal documents, then use web search to find information from the internet. After using both tools, provide a comprehensive answer that clearly separates the findings, right? So basically the response that we are looking for is the agent should respond by saying based on internal data, this is what the agent found. Based on web search results, this is what the agent found. And then again, we are kind of padding this towards the end. Sometimes a best practice that even though we've said that, use both tools, but we are reinforcing that, saying always use both tools before giving your final answer, right? That's a good prompt engineering practice. This is the binding step that we were talking about. So LLM with tools variable we are going to create here, and we are going to call it LLM dot bind tools. So what this does, there are two tools within, or the agent has access to two tools. But if you see when the agent gets initiated, so when the state is kind of at the initial stage, it's actually the large language model that is doing the thought process, because the large language model is taking a decision based on the user query and the system prompt that we are passing to understand what tools does it have access to. Now, if you just quickly go back to any of these tools, one of the most important things that we do within this tool definition function is we always annotate what is exactly this tool going to do. So in this case, we are saying search OpenAI vector store for relevant PDF chunks from internal recipe documents. Now the large language model actually has access to this information, right? So it has a description available for each of the tools that we will bind with that large language model. Same goes for the web search. So what is really happening here is you are just making sure that the large language model has understanding that these two tools exist. The execution of the tools is not happening here. The LLM is only making a decision to understand which tool to use, and then basis of the decision that it makes, that graph will traverse through the right edge, which takes them to the right tool. So it will not go to end if it identifies that, okay, the user question demands that I should use one of these tools. It will actually kind of think and say that, okay, this is the tool that I would use. And basis of that, the graph would traverse to the node where the tool exists. So agent node with structured output is the next thing. So basically here we are going to define the agent node. Again, if you remember that uh, presentation that we saw earlier, there was an agent node. So the agent node and then state is agent state. So here we are just going to print agent thinking, message is equal to state messages. Now this messages is very critical because we'll have to keep maintaining those messages and that state so that this entire thing can work. Next, we say that if not any is in instance message system message for message in messages. So basically, we're just looping through this messages list to understand if system message already exists. And the reason why this condition is put in is because the system message or the system prompt needs to be provided only once within the state. Otherwise, it will keep adding that system prompt again and again and again, which we don't want, and that's why we're just putting this kind of check. And then we are saying response equal to LLM with tools invoke messages. So here basically the LLM with tools is getting invoked because now that LLM knows what tools I have access to, and it will provide some response based on the user query system prompt, etc. Then we have the tool execution node. So the execution part happens at the node. Once you are at that specific node within LangGraph, that's where the actual execution would happen. So for that, we are defining that, okay, there are tools, RAG search and web search, and the tool node is equal to tool node, and then we are passing this list for tools. So then it understands that there are these two nodes where tools exist. Hmm. Then we say define should continue. So basically what this would do is for every iteration through that entire process, right? So initial message or the user message, there's the system prompt, human message, AI message. Every time this loop completes, the agent should take a decision whether it needs to continue or it needs to end. So here we are passing literals to this specific function, which means that we are controlling or we are putting a very strict control on the agent to only have two outputs. So this function can return either of these two things. Either it can return tools or it can return end. And that's the decision that the LLM would take. If it is tools, then it will again go back to one additional tool. If it is end, it will just end that particular message state and then provide the final response to the user. So message is equal to state messages, last message, message minus one. So this is basically just Python way of saying that, okay, what is the last message in the list? Minus one basically means the last message in that particular list. If there are tool calls, continue to tools. So this is basically if has attribute, last message has tool calls, and this is again double checking, right? So it's one, it is checking whether the tool call exists within my messages state, and it also decides or checks whether that is a non-null entry, right? So it could be that it has something called as tool calls, but actually there is no content within that, right? So it checks for both those conditions, and then it says that, okay, if tool call detected, then tool call name for tool call in last message dot tool calls, and then it will return the tool that needs to be used. If no more tool calls, so like we said, tools is one kind of output, other is end. So if no tools found, then just end this particular should continue function. Now we actually start building the graph. So we say graph equal to state graph, and then we pass the agent state. We add nodes explicitly calling that, okay, we have one agent node and another tool node. Right, so if you see here, tool node is basically this list of tools. An agent node is this particular part of the code. Hmm. So we pass those as nodes. We also need to pass edges. So basically graph, add edge, and we put one kind of first node called start. From start, it's going to travel to agent. So this is a edge. So basically it's kind of telling you that from one node to the other, and that's why we are calling it an edge. And then we add a conditional edge. So that should continue function gets invoked here, where the agent is going to check that what is the output from that particular function should continue. If it is tools, it needs to traverse to the tools. If it is end, it needs to end that particular state and then provide the response to the user. So graph dot add edge, we do tools agent. So this is basically if tools get invoked, then again we give one node, and then what we say that okay, tools execute the tool and then pass it back to the agent. Finally, we do our app variable. So app equal to graph dot compile, and then we have the actual execution of our program. If name equal to main, initial state equal to messages, and then human message is what we're going to pass, and say content equal to show me the recipe for vegetable spring rolls. And these are just formattings. Final equal to app dot invoke initial state, and eventually we'll kind of print out the message. So let's run this so that it becomes a little more clear. So I'm going to run langgraph or lg agent dot py, and let's hit enter. Right, so if you see agent thinking, tool calls detected, so RAG search and web search. The first thing it is doing is RAG search called with query vegetable spring rolls recipe, web search called with query vegetable spring rolls recipe. It also prints web search result. Let me just go up. So web search returned 3 results. RAG search returned 1 chunk, right? And generally, if you put something like max results or k equal to 3, it should result in 3 chunks. If you remember, we've also put a threshold on the similarity score. So basis of that threshold, it only found 1 chunk that is relevant. So if you see, this is like one loop. It's gone through one loop. And after the tool got executed, we added one edge which says tool to agent. So it goes back to the agent. Agent again thinks, and this is where the should continue function gets invoked. What the agent decides at this point is whatever information I have available right now is sufficient to provide the response to the user. Hence, it goes to the end node, and basis of that, then it will provide the final answer. So if you see the final answer, we had put prompt, a very, very explicit prompt stating very clearly how we want the format to be shown. So it says based on internal data, which is RAG, this is the recipe for your spring roll, vegetable spring roll. So it gives you a detailed recipe. And then based on web search results, several online recipes for vegetable spring roll provide variations and additional tips. And what it is showing is, okay, this is 1, this is 2, this is 3, and then it also gives you the links that where exactly you can go and see the full recipe. This is the state, right? So I wanted to show you that message state, how it would look like. So if you saw, we initiated the state with the human message, which is show me the recipe for vegetable string rolls. Then the AI message, where the AI message decided that, okay, I need to call a tool for this, right? So there is a tool call. Then you have the tool message. This has been kind of restricted to only 100 characters, hence it's ending here. But actually, it is a pretty big chunk of text that is coming back from the tool message, right? Then you have another tool message, which is probably coming from the web search. The tool then passes it back to the agent, and that's why you can see AI message based on internal data RAG. The recipe for which spring rolls includes the following. I hope this clears, how exactly this works under the hood. RAG is really, really adding a lot of value to enterprise use cases as well, because there is so much of knowledge, especially in unstructured format, which is like your PDF, Word, uh, images, videos, etc. Right? And okay, so multi-model RAG, which kind of takes into consideration images, audio, video as well, is a slightly more complex implementation, because if you see any of the models that we used so far in this particular video were text embedding models. What that means is the models have the capability to understand, embed, and store text, right? But you need different kind of either techniques to manage multi-model content like audio, video, or you need embedding models that are multi-model in nature. Right? That's something that we probably won't be able to cover in this video. After this, there is just one more script, which is the Streamlit app. I think at the beginning of the video, I kind of showed that app. So what I would suggest is you go through that particular uh, code on your own and try to make modifications and see how you can further improve that application. Last thing I want to say is here we have kind of, built the blocks for something called as deep research. So if you go to something like ChatGPT or Gemini, you would see that deep research is becoming really, really popular. Basically, you ask some uh, LLM to do a very detailed research on a particular topic. That entire concept works on RAG and a combination of web search along with this agentic approach. So that's something that we'll cover in the next video. So it's going to be a continuation of this video, but we right now have all the building blocks, or rather most of the building blocks that we need to build a deep research agent as well. So thank you so much for watching. It was a pretty long video, but I wanted to be as detailed as possible to help you really, really understand the concept of RAG and then see it in action as well. See you in the next video. Thank you so much.